Well, hello, good afternoon, everybody. Welcome to today's talk, where I will talk about, I will give you an introduction into the new concurrency model of Java and tell you about some of its pitfalls. My name is David Vlijmincx. I am a software developer at Team Rockstars IT in the Netherlands, and I have been developing software using Java for around 7 years now. And in my free time, you can find me on my Twitter or via my website, where I write mostly about unit testing and about structured or about concurrency, especially about Project Loom, which is also the topic of today's talk. So here you have a quick outline of what I will cover today. I will start with what the current situation is in Java, how we are currently using structured concurrency and how it is implemented. And then I will switch over to virtual threads, which are a new addition. They are in preview with Java 19. And about structured concurrency, which Loom also added as a preview feature to Java 19. And at the end, there is some time for a Q&A. So if you have any questions, please don't hesitate to ask them. We are going to cover a lot of new ground today. So some of it may be very new to you, and well, it's not to me, but just enter the code GeeCON 2022 and select room 6, and then you can upvote the questions so I know which one to answer the first at the end. So before we start, a word of caution. Project Loom, the virtual threads, and structured concurrency are still a work in progress, which means they can still change in the future. So with Java, every API I will call today, that you will see on the screen, those will work with Java 19, but they are subject to change, so they may change slightly or heavily with Java 20, but the ideas behind them should stay, somewhat similar. So this is how we currently create a single thread in Java. Somebody raise their hand if you ever tried something like this before. Lots of hands. That's very great. Did somebody also try to create already some virtual threads, played with them? Great, at least 3. So lots of you guys also I will see lots of new stuff. And the 3 guys who raised their hands, I hope you also learned something new. So in Java, we call the constructor, constructor, and ask it to create a new thread. In this example, I passed it a runnable called task. I get a thread object back, and I call the start method. And then Java will start running this thread for me. So what happens behind the scenes is that when I call this constructor, Java will ask the operating system, can you create a thread for me, a kernel thread? And the operating system will do this, but while it does this, it will also allocate 1 or 2 megabytes of memory, which is quite a lot, and maybe not every thread is going to need that much of memory. So as you can imagine, calling the operating system from the GVM, so we have to exit just GVM. We have to go to other operating system, which takes some time. It's not as quick as just creating a Java method itself. So we have this this task that takes some duration to perform, and we have to allocate some memory that we maybe not going to use all of it. So combining those 2 things, and especially the memory usage, if you would do this like 1 million times, creating this thread, you would also need to allocate 1 or 2 megabytes for each thread, which would end up being 1 terabyte of memory, which is quite a lot. And I tried it on my laptop, it crashed into the ground. So you can try this at home, but I don't advise it. So because we can't have a lot of them, especially because the memory usage, we consider these threads to be very expensive because they are a sparse resource. So let's see how we can use them inside Java. I created just simple illustrations to keep it simple. And at the top I have 3 tasks, and for every task that I have, I will also create a virtual or a thread. So this is, for us developers, is a very easy way to develop, because we can just create a thread when we need to, and discard it when it's finished running. Well, this is very easy for us. We are not making great use of our hardware, because we are doing this very long taking call every time, and we're going to allocate some memory that we will, that we are going to destroy later on. So, while this is very easy for us, it's not the best use of the resources. So the next best thing is to use something like the executors or a single thread pool. So at the right, I have a simple illustration of a thread pool, which has 3 threads inside of it, and I submit tasks to this thread pool. When I submit a task, a thread that is available will pick up this task, will start running it, and when it is done, it will be put back inside the thread pool. And will wait for a new task to pick up, if one is available. We now make better use of the resources because we are not going to create a thread every time. We just cache them inside this thread pool, and we don't destroy the threads because the new task will use it. But using a thread pool has a few downsides. For example, the thread locals. If you have a task that sets a thread local on that thread, and the thread will start running, the task will be performed, and you forget to unset this thread local, the thread will be put back inside the pool, and a new task will be able to read this thread local. So at that moment, you are leaking your thread locals into other tasks, which isn't appreciated. And there's also the case that when you have a thread, and it starts running some task, and this task needs to call your file system or some REST API. At that moment, that thread is also blocked. And when it is blocked, it isn't doing anything. So now we have this very expensive resource that isn't doing anything, which is also kind of a waste. And of course, we have thread leakage. If the parent thread that created this thread pool throws an exception, it will be cancelled. Then we have these threads that still have a task, still running. And we leaked our threads inside the system because there's nothing to control them anymore, which also isn't that nice. And then there is async programming. Async programming tries to resolve the issue of making better use of our hardware. It really does so, but you're going to create callback after callback after callback, and slowly you will enter what is called callback hell. Some of you may know it from JavaScript. And in my opinion, it's very hard to write, but it's even harder to read because you will have these long methods that will act like some kind of pipeline. So virtual threads try to solve all of this. A virtual thread is nothing more than just an alternative implementation of the thread class. So it's just a concept that lives inside the GVM. So when we later on will create a virtual thread, there is no call being made to the operating system. The operating system doesn't know about them. So now we don't have to make this very expensive call, which is the first improvement. And because they are just a concept that lives inside the GVM, we also don't have to allocate the memory, or the operating system doesn't have to allocate that memory, because we will just do it inside the heap. So the great thing of doing it inside the heap is that it now can grow the stack frames, so the memory the thread uses, can now grow and shrink as it needs to. But the thing to keep in mind is that now the stack frames live inside the heap. So if your stack frames grow, also your usage of your heap space will also grow. So with the previous threads that we are currently familiar with in Java, the now called platform threads, they will store their stack frames inside the 1 or 2 megabytes that is allocated by the operating system, while virtual threads will store it inside the heap. So because it doesn't use that much memory and making them is very fast, we consider them to be very cheap. They're almost as cheap as creating a string would be in Java. So here I have this very simple illustration. I really like arrows, as you may have expected. And at the top, I created arrows that should represent a virtual threads. So I created a bunch of virtual threads. And you may be wondering if I can, they don't take up that much memory. Can I create 1 million virtual threads? Yes, you can. But then you may start wondering, I have this 1 million threads. these million virtual threads, but I don't have this system with 1 million cores. I don't think anyone has those. Or it's maybe some very expensive AWS instance, but you're probably, it's a waste of money. So now you have these virtual threads at the top, and they run on what is called a carrier thread. So I have the virtual threads at the bottom, and the carrier threads, the virtual threads at the top, and the carrier threads at the bottom. And these carrier threads are nothing more than just your normal platform threads, but they carry out the work of your virtual threads. So they are now mapped many to many. You have many virtual threads and many carrier threads. And you'll have as many carrier threads available as that you will have cores available. So if you have a 4-core system, you will have 4 cores or 4 carrier threads. If you have more cores, you have more carrier threads. So how do these map? A fork join pool is used. So every carrier thread will have a queue of virtual threads that it has to run. But as you will notice, the last carrier thread has none. And that's where the work stealing schedule comes in. When a carrier thread is done running all its virtual threads, it will just steal a virtual thread from another queue. So every carrier thread is always performing some work because they are the most expensive resource. So now we still have, well, some carrier threads mapped to, or some virtual threads mapped to carrier threads. So how does each virtual thread get some time to run? Well, each carrier thread is, of course, assigned a virtual thread, and this carrier thread will start running this virtual thread until either the virtual thread is finished or it encounters a blocking method. Only in those two situations will it be unmounted. So let's, for example, take that it will be blocked. The virtual thread is being blocked. It will be unmounted from the carrier thread. So the stack frames that live inside the carrier thread will be copied back inside the heap. So this carrier thread is now empty, and the new virtual thread will take its place. So that virtual thread's stack frames will be copied inside the carrier thread. This makes blocking very cheap, because blocking isn't being done on the carrier thread. It happens all inside the queue. So this carrier thread is now always running a virtual thread that isn't blocked. There are some points you have to watch out for. For example, as I have said, when you encounter a blocking method, it will be unmounted. But not every method is ready yet. As I have said, Project Loom is still a work in progress. So here I have 3 methods. The synchronize block, the object.wait, and some random call you may do to native code using GNI. In those cases, there is a memory pointer inside the GVM that is being used, and at that moment, a virtual thread can't be unmounted. So what it is, it's being pinned. So a virtual thread is then being pinned to its carrier thread, which means that it can't be unmounted. So both the carrier thread and the virtual thread will be blocked. So when you will use virtual threads, maybe after this talk, please don't use these yet. So this is the thing you really want to see, and that's how the API has changed. So at the top, I have this thread class, and I will call the new start virtual thread method. It takes a runnable as its parameter, and after this line, a virtual thread will immediately start running. And in the second example, the one at the bottom, I use the new builder method, the thread.ofVirtual. There's also a thread.ofPlatform to create platform threads, but those are the old, and in with the new. And with the new builder, you can use it to set some properties. For example, the name. So I will create a virtual thread. I will give it the name virtual-thread, and I will give it an unstarted task. So I will get a thread object that I will have the start method. I have to call the start method later on. And as you can see, both of these two methods return a thread. So virtual threads are backwards compatible. So your current code or your old libraries can still use virtual threads even though they don't know about them. So they can still benefit from the performance improvements. And since Java 5, we are encouraged to use the executors instead of the thread class directly. So here I have the new virtual thread per task executor. It really does what the name says that it does. It will create a virtual thread for each task that you will submit to it. Another nice thing with Java 19 is that the executor services now implement the auto-closable interface. So now I can put them inside a try. So here I have this complete example where I will now use the executor service and will submit 2 new tasks. And each of these tasks will run in a new virtual thread. This new executor service doesn't pull the virtual threads. It will create a new one every time. So now you may be wondering, I have this old executor service that I really like. Can I also use it with virtual threads? Yes, you can. All you have to do is to create a thread factory. So here I have this thread factory that I will create using thread.ofVirtual.factory. And this factory will create a virtual thread each time. So here I have 3 example executor services. And I will pass this factory as a parameter to each of them. It will work with all of them, but then my slide will be very full. So now some of the pitfalls. As I've already said, you don't ever want to pull virtual threads. They are really meant to be created when you need them and to be discarded when they are done. Also using thread pools. You may now think, I'm going to replace my old executor service with the new one. That could lead to some problems. Let me explain this with an example. For example, you have now this current executor service that uses 5 platform threads. And you submit tasks to it to call this external system. So at any point in time, though you will only have 5 concurrent connections to this external system. But with virtual threads, if you submit a task, the carry thread will start running. It will call this external system. It will be blocked. At that moment, the carry thread will pick up a new task or a new virtual thread. And this will also make this call to this external system. And you can go on and on like that. So at one point, you will have a lot of concurrent connections to this external system. So my advice would be to use something of a log, like a semaphore, to prevent DDoSing that other system. And the other one is that old libraries may not have been adapted yet. You may start wondering, but he said they were backwards compatible. Yes, they are. But there are maybe moments where the old library, the old library is written with the idea that threads are very expensive. And now these virtual threads are very cheap. So it may not use them in the right way. So you may have some performance improvements if you make better use of these virtual threads that are very cheap. And of course, the old libraries may use a blocking method that isn't supported. So then you will just have normal threading. So now you can create lots of threads, like 1 million or 10 million of them. And now the next thing is, how do I manage all of these threads? And to do that, I want to talk about structured concurrency. But before I will dive deep inside what structured concurrency is all about, I want to start with a very related object, and that's structured code. So here I have this very simple, Java method. It's, in my opinion, very easy to read. We will start at, a thread will call this method, method A, and method A will have 2 other methods, method calls inside of it. It will call method B, and it will call method C. Both will return some value, and before I exit method A, I will combine these results and return them to the caller. So there's this very easy way of reading the code. We'll start at A, then we will go to B, then C, and then we will have a result. The great thing about structured code is that if method B throws an exception, at that point we will just stop. We have called method A, we tried method B, but method C will never be called, and we won't try to create a result. And the same goes for method C. We will call method B A, then method B. Only then we will find out method C has thrown an exception, but we will never try to create a result. So it is very clear when a method will start and when one will finish. So let's now take a look at the same example, but with threads. Again, I have here method A at the top. Then I will have a method B that will start some thread and will return some value in the future. And I have method C that will also try or also runs a thread to get a value for bar. And then I will wait first for food to finish, and then I will wait for bar to finish. Well, some of you may have noticed the arrows in the right corner. Now B and C will run concurrently, so we will start at A, B and C will run at the same time, and then we try to create a result. So some of you may know what's coming next, and that's that B has thrown an exception. And at that point, C will happily continue running. We will find out at the foo.get that bar of that the method B has thrown an exception. And the same goes for method C. If method C throws an exception, method B will happily keep running. We will even wait for it at the foo.get. And when we will get at the bar.get, only then we will find out that C has thrown an exception. So we waited unnecessarily long for food to finish. It could have been cancelled. And of course the same happens if the handler thread of this method fails, throws an exception, then both B and C will happily continue running, but there won't be a method to return a value to. So this is where structured concurrency comes really in. We want to have a structured way of working with threads. So we know when a thread will start and that they are done running at the end of our code. And in my opinion, they are a great and more powerful improvement over the executor services. So let's see how we can use structured code. I have here this try with resource statement, in which I will create a new scope. So to use structured concurrency inside Java, we use this structured task scope class, and it has two built-in shutdown policies. We have the shutdown on failure that we see here, and the shutdown on success. And the shutdown on failure really behaves the same as the invoke all method that we know from the executor services, in that we will start a bunch of threads, and either they all finish, or if one thread throws an exception, all of them will be cancelled. So here I will use the scope object, because the scope will manage these threads. We use the fork method to create two new virtual threads. So here I have one to get the account information and one to get the orders. So both of these will run in a virtual thread. And then they will start running, and then this parent thread will block. At the scope.join, we will wait till the criteria of the shutdown policy has been met. So in this case, both of these threads finish, or they are cancelled because one has thrown an exception. So for example, if the orders thread has thrown an exception, accounts will be cancelled. So let's continue this code. So let's think both of these threads have finished correctly. Then we will continue, and we will see the scope throw if failed. And at the throw if failed, we will check, or we will propagate the error that one of these two threads has thrown. If none of the threads have thrown an exception, we can continue. And we can create the result that we want. So you see that we use features at the top. So you may have been expecting to use the get to get the values, but within structured concurrency, we really want to use the result now. And we do that because at this point in our code, we know that these threads are finished. At the scope.join, we have already waited. With the throw if failed, we know that there is no exception being propagated. So at this point, we can immediately get the result of both of these features. So, as I've said, there are two built-in shutdown policies. And the other one is the shutdown on success. And the shutdown on success behaves the same as the invoke any method of the executor services. I will start a bunch of threads, and I'm only interested in the first thread that finishes. So it really looks the same. I again have the scope object that I will use to fork two new virtual threads. One to get the price of shop 1, and one to get the price of shop 2. Again, I will use the scope.join. I will wait till my first thread is finished. So if shop 1 returns a value first, then shop 2 will be cancelled. And then I will continue. And then I will get to the last line, where I will get my result. And to do that, I use the scope object, because I don't know at this time which one of my futures has finished first. I can check both of them, but that would take more typing. Or I can just use the scope object and call the result now method, and the result method, and it will return the result of the first thread that finishes. So another thing that is very easy with structured concurrency in the structured task scope is that you can create deadlines. And it all looks the same as the 2 slides back, where I will create 2 threads. But instead of calling the scope.join, I will call this join until method, which takes an instance as its parameter. So here I have this join until, and I pass it an instance of 10 seconds. So both of these 2 threads, these virtual threads that are running, have 10 seconds to finish. If they don't, a timeout exception will be thrown. And if they finish in time, the code will continue as normally. So the pitfall really is doing it yourself. The structured concurrency, when it hits production, you should really give it a try. It's a very powerful way of managing the lifetime of threads and preventing them leaking inside all your code. So I have talked a lot about what happens behind the scenes and how it all works. So I don't want to scare you off. It's very easy to start with virtual threads. All you have to know is these 2 methods. The first one will create a virtual thread and start immediately running your task. And of course, the one that most of you will probably use is the new executor service with its very clear name. Well, thank you for listening to my presentation. If you have any questions, you can always find me on Twitter or via my website. And let's now go to all the questions on Slido. Which are a lot. Can you compare virtual threads to Kotlin coroutines? Is there any performance advantage of using virtual threads over coroutines? Yes. Coroutines don't work in Java, so that's the first one. So that would make it very easy if you're just using Java. I never tested or compared them really. The second questions, are virtual threads and fibers the same thing? Yes, they are, but fibers is the old name. Virtual threads are the new name, and it really comes from the virtual memory that we virtual memory. It isn't real memory as it is, memory. So that's where the virtual part comes from. So fibers were the first names, or the first name being it was first mentioned inside the I lost the word for it. It doesn't really matter, but so let's just go to the second question. You mentioned synchronized block and others like object wait are not supported. Is it only temporary issue present in Java 19? Or is it a permanent problem? That I don't know. The current problem is that it uses a pointer in memory, and because the heap is copied in and out of this carrier thread, the memory pointer will, well, change. So that's how I believe what the current problem is. So I hope they will fix it, but I'm not part of the team developing it, so it's hard to answer. How do you configure the number of available carrier threads to hold the virtual threads? You don't. There was a way to do it with previous Java versions. There is a way?
Yes, there is a system property.
There's a system property. That's great. I looked at previous examples where they use a different kind of thread pool, but that option was taken out, so maybe it will be put back in the future, but until then there is a property. Does thread local and thread IDs still work similarly? That question, I don't really get it. They do. Oh. Okay, so you can just opt out and further they just work the same way. It's very nice. What will happen if the blocked... does the thread... No, I had that one. What will happen to the blocked virtual thread in case of an interrupted exception? I never tried it, but because it is blocked, it isn't really running. So I wouldn't really know what would happen, but it's something that I would love to try after this talk. Will a long-running virtual thread be unmounted from the system thread after some maximum allowed of time? No, it will just continue running till it's done, or it encounters a blocking method. Can we have some data leaks when the same virtual thread is changing to... I also don't really understand this question. I don't think so, because, well, I really wanted to try the extend locals, but it wasn't in Java 19 as a preview feature, so maybe that solves the problem, but I'm not sure. How does Java code signal to the JVM that it's performing a blocking operation? That's a very good question. Most of the blocking methods have been rewritten, so they are aware of what a virtual thread is. So if you, for example, step in a thread.sleep, the thread.sleep will check if it's a virtual thread, and if so, it will call a other kind of special scheduler, but the methods just have been rewritten to be aware of virtual threads. How can I use this with Project Reactor? Never tried Project Reactor, so I don't really know. Some people here say you don't, so just use virtual threads, I guess.
Programming and virtual threads do not really combine well, so
you don't want to. It's even better. Why is throw a field necessarily before join? Should join not throw the exception itself? It's not necessary, but it's just nice to know if one of those threads have thrown an exception. I think it will just swallow the exception, but I never tried it. Can I nest scopes? Can I access scope from subtasks? Yes, you can, but then it will throw an exception. The parent thread, as it were, is the only one who is allowed to... No? Yes, you can use a new structured task scope inside that thread, but you can't use the old scope inside the new thread. Won't it throw an exception when you try to access things? We should try. So, okay, I just had that one. What thread pool is used for structured concurrency? A fork join pool, if I remember correctly. Can I nest scopes? Can I... what scheduler is used for virtual threads to carrier threads? All I have seen mentioned is being a just used for virtual threads to carrier threads. It's a combination of the work stealing scheduler and the fork join pool. That's kind of this combination that manages which virtual thread is being run. Assuming stuff that doesn't work now in virtual threads will work later. What would be the downside of using virtual threads over platform threads? One of the downsides is that the stack frames now live inside the heap, where they with platform threads they live off the heap. So it's quite heavy for the garbage collector because you will now use more heap space. So that's one of the downsides. Is there?
Okay, we are answering only questions with two upvotes or more, and just try it. Yeah.
Okay. Is there a count limit virtual thread pool? Not that I'm aware of. Maybe if you use one of the old executor services together with virtual threads, but I don't think so. The idea really is that you create virtual threads just when you need to. And you can just control the amount of virtual threads running at the same time using this parameter. Is the file descriptor shared between virtual threads? I don't know. Never tried it and really should, I guess, after this talk. In which order are virtual threads executed? They are executed in a way that they will be submitted to a queue. A carrier thread will, of course, pick up the first one. When it's being blocked, it's put back at the top of this queue. So when a carrier thread is ready, it will pick up the virtual thread from the top. So it's the last in, first out. Is a thread attached permanently to a single carrier thread, or could it be bound to different ones during its life cycle? It's mapped many to many, so every virtual thread can run on any of these carrier threads. At one point in the presentation, if one carrier thread, for example, doesn't have any virtual threads to run, it will just steal a virtual thread from another queue and will run that one. So at that point, you will also share virtual threads between carrier threads. Fork join is apparently very bad for I/O. Any alternatives? For as far as I know, you can't change the pool. You could in previous versions, so I don't know if it comes back. But the great thing about virtual threads is that they are very good at waiting, so you can just have lots of them waiting at the same time. So maybe that fixes it some way.
In this case, actually, fork join is not doing any I/O. That's the trick. So when the blocking operation comes, the fork join is not. Carrier threads are not doing any work. So that's the trick. So it's not an issue in our case.
Okay, so it's not an issue. How to check that a library or framework does not use the unsupported features like synchronize? Is there some list of supported libraries? There is no list that I'm aware of, but you should just really try it out. It's in preview after all. So I would encourage you just trying it out and see if I see someone waving.
Yes, there is a way. You have to just go and use like a system flag.
Yeah. Okay, so you just have to set a system flag and then it will work.
And then it will just open the standard output that the virtual thread goes in. So that's the way.
And then you will see which virtual thread is spent. Okay. It's a really nice solution. And how to check? I should only do the ones with 2 upvotes, so.
Okay, then I guess so as long as there is no more upvoted questions, we can end the presentation.
Well, thank you for listening.